Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show design analysis and optimization of a surface condenser used for power plant. Actually, in power plant we are having a lot of exhaust steam and that can be replaced as a condensate using this surface condenser. This is the location. From here we'll be supplying exhaust steam, and this is used to create a vacuum inside this shell, and this is the location from where we will provide cold water. And you can see here, this is one barrier, or you can say like plate, which will be working as a barrier for this cold water, and cold water will be passing through these tubes. Surrounding these tubes there will be hot steam, right? So the exhaust steam from this power plant will be converted to condensate, and that will be collected from here. So this is the condensate collector. Will be having reduced amount of heat and temperature from the exhaust steam. Okay, now for simulation we have to make the model as simple as possible. So we will remove these nut and bolts, etc., and by the same time the back side we have made this copper tube two ways, so that one will remove it. We'll make this copper tube as a single pass copper tube will be utilizing. Okay, so without wasting time, let us move on to the next model for simulation. Okay, and we have to get the single model. This is a single pass model. This is exactly the same thing. What we have done for simplification of this simulation, we have removed the base, and the bent tube end we have converted this one as a straight tube. Okay, the leads have already been provided at all the different locations. For starting this flow simulation, we have to create an environment, and that will be done using wizard. Keeping the name of the project as default project 2, and we're keeping the system as SI system, and temperature will consider as degree centigrade, and pressure will consider as megapascal. Next, this one can be considered as internal analysis, but we want to consider the airflow outside also. That's why we want to take this analysis as an external one. We want to consider convectional heat transfer at the outer surface from the shell to atmosphere. So external analysis we are considering, and the internal cavities we will consider. So these things we are not checking in. It is heat conduction in solids, and definitely gravity will be involved. You can see the direction of gravity. It will be in the y direction, so along y it will be minus 9.81 meter per second square, and along z direction it will be 0. Next, so default fluid will be taking air and steam, and will provide cold water for reducing the temperature of steam. We're taking air as default gas, which will remain outside this surface condenser, and we're considering steam also as main fluid, and we'll supply water as a coolant. So let us take water also as a liquid. We are taking water. So you can see 3 different fluids we have taken. We have taken steam and air as a default fluid, and for coolant we are supplying water at low temperature. Next, the material we are considering default material as copper. Next, we are considering default roughness values. Next, temperature will be 20 degrees centigrade, that is atmospheric temperature. Similarly, the solid parameters, the temperature will be, that is the shell temperature will be 20 degrees centigrade. And let us see concentration. Steam, actually the outside is completely filled up with air, so concentration of air will be 100%, that is concentration of air is 1, and steam will be provided from outside, so it will be provided during actual application of boundary conditions. So at this moment the concentration of steam will be 0. That means we are providing steam from outside and cold water from outside, and the maximum domain is filled up with air, which is remaining outside this surface condenser. Let us finish this one. You can see this is the computational domain. This is very huge. We have to reduce this volume, because more the volume, more is the time for calculations. Let us edit this computational domain. Now our computational domain is ready. Green check. This is our computational domain. So let us hide this part. We have to apply fluid subdomains. And for application of subdomains and boundary conditions, it is better to have a segmented view of this model. So we'll cut it along front plane. Let us see the fluid subdomains. Insert fluid subdomain. We have to supply steam from this location. So we have to select that location. And the thermodynamic parameters of steam, which will be 100 degrees centigrade. We'll supply steam at 100 degrees centigrade. So the domain for steam is defined. Next one, we have to provide the domain for cold water. Fluid subdomains, insert fluid subdomain, and we'll take water. So we'll provide cold water at 0 degrees centigrade from this location. So this is the fluid domain for cold water at 0 degrees centigrade. Green check. Next one, some atmospheric boundary conditions should be required. Insert fluid subdomains. Fluid subdomains have been defined properly. Next one, we have to apply some boundary conditions. So insert boundary condition, and we have to apply steam at a rate of 1 kg per second, and temperature we can see from here. Thermodynamic parameters, it will be 100 degrees centigrade. Steam at 100 degrees centigrade we are supplying. And let us see the substance concentration. It will be 100% of steam, and air will be 0, right? So we're providing only steam from outside. No air is being supplied inside. Air will be flowing outside this surface condenser, and steam will be passing from this location at a rate of 1 kg per second. It is defined. Green check. Next, we have to apply cold water from this location. Boundary conditions. Insert boundary condition. We have to provide cold water at 0 degrees centigrade, and mass for it we want 5 kg per second. Thermodynamic parameters. Let us provide cold water at 0 degrees centigrade, and substance concentration, it will be 100% of water. So we're considering concentration of air as 0 and steam also 0. So we're supplying water from this location at a rate of 5 kg per second, and temperature of water will be 0 degrees centigrade. So this is required to extract heat from the steam, because initially steam will be converted from gaseous phase to liquid phase, then only temperature will be reduced. It may so happen that throughout this assimilation, the temperature of steam may not be reduced, because for condensation of steam from gaseous phase to liquid phase, a lot of heat to be extracted. So both the boundary conditions have been applied. Next one, we have applied boundary condition for this atmospheric conditions. Insert boundary condition. It will be atmospheric pressure at this location. Green check. 2 more boundary conditions are required at 2 different entries. Again, insert boundary condition. It will be atmospheric pressure at the exit of cold water. Green check. And another boundary condition is required. That means we want to provide vacuum inside this shell to have a free flow of steam inside this shell. So insert boundary condition. We want to provide at this location, the pressure will be very less. Let us provide pressure equal to 0.006 megapascal pressure we are applying at this location. That means vacuum is created inside this shell. You can check. We have considered this one as an external analysis. So we want to consider a convectional heat transfer rate from the outer shell to the atmosphere. So another boundary condition is also required. Insert boundary condition, and we want to consider heat transfer rate from the shell. Let us consider that convective heat transfer coefficient equal to 100 watt per meter square degree Kelvin. I have to select the surfaces for this convective heat transfer rate. Then check. So all the boundary conditions have been applied properly. Next one, we want to go for some goals. We have to define some goals. Let us insert some surface goals. We want to have temperature and pressure at this location. By the same time, temperature and pressure at this location also. Right? So select average temperature of fluid and average total pressure at the exit of hot water. Green check. 2 more surface goals are needed. So insert surface goals. It will be average temperature of fluid and average total pressure at the exit of cold water. Green check. So all the boundary conditions have been applied properly. Now we can run this simulation. Okay. So let us run this one. The solver window has started already. It is showing that solver window has finished its iterations. After 293 numbers of iterations, the solution is converged. We can see here the 4 goals we have already achieved. That is, temperature of exit end of cold water is 32.24 degrees centigrade. That means it has gained a huge amount of heat, but the thing is, like, steam temperature has not been reduced because steam was 100 degrees centigrade, so it is still in the gaseous phase. So we have to provide more cooling to use condensate at lower temperature. And by the same time, we can see the temperature difference. Temperature at the exit of cold water is 0.08 megapascal, and at the exit end of hot water is equal to atmospheric pressure 0.101276 megapascal. It is near about atmospheric pressure, but at the end of cold water, pressure has been reduced. Now we can see all these things results from the cut plot also. Let us see our cut plots from the results. Cut plots, insert cut plot. First of all, we want to see temperature of fluid from front plane. Green check. So as we have considered this one as an external analysis, you can see the flow of air outside, at the same time flow of steam and cold water inside also, right? So better to see these things in the form of an animation. Cut plot 1. Let us play. It is showing the temperature outside this shell. It is in the range of blue color. It is in the blue range. That means temperature is near 6 to 7 degrees centigrade. And inside this shell, the color is in the green zone. That means still it is in the range of approximately 100 degrees centigrade. You can see how convection is occurring outside this shell. From the shell to the atmospheric air, how heat is being transferred by way of convection. Now see some other thing. We want to see surface plots. So let us clear and hide this part, and we want to see surface plots. Insert surface plots. We want to see temperature fluid with all phases. It is showing variation of color at different locations. At the 2 entries and exit location, the temperature is less because steam is not supplied at these 2 locations, and steam is being supplied from this top location. So all the location excluding the entry and exit, temperature is very high. In this case, you can see the temperature is near about 98 degrees centigrade, 98.14 degrees centigrade. Approximately the temperature is in the range of 100 degrees centigrade. You can see 98.4 is there. but in the cold region the temperature is very less, right? Okay. Next one, we'll see the dynamics of these flow particles inside this shell. So we should go for flow trajectories. Before that, we should clear and hide this part, and we'll go for flow trajectories. Flow trajectories, insert, and here instead of 20 numbers we want to see more numbers. Let us say 200 numbers, and instead of pipes we want to see in the form of arrows, and we want to see temperature fluid from this location. Select other, lead number 16, green check. Now the particle study is still running. It will take some time for getting the results. Now it is visible how the cold water particles are moving inside. Right, at this location here there is a huge concentration of cold water before entering into this shell. And let us play these things. Flow trajectories, play. You see how this cold water is passing through these small tubes. You can see at this location some kind of circulation is there. Water particles are being gathered at this location. Too much of concentration of water particles at this location. Let us clear and hide this part. Next one, we want to see the combined flow trajectories of steam and cold water. For better selection, let us cut this one from front plane and we can apply specific location in a better way. So flow trajectories, insert flow trajectory, and instead of pipes we want to see in this form of arrows. Let us make this one as 100 numbers of arrows, and we want to provide location. It will be cold water will be passing from here, from phase 1, and steam will be passing from this location. So phase 1 and phase 2 is selected, green check. Particle study is running. You can see the path of steam. But at the same time it is showing that because of vacuum it is going outside, and some steam particles are coming inside also, inside this shell. So from this design it is clearly visible that vacuum should be provided at the bottom position, not at this location. So this is a faulty design, I think. Vacuum could be provided at this location to have a better flow of these steam particles, right? So I don't think any meaning of providing any kind of parametric study with this geometry. We can change the geometry, then we can go for parametric study and go for final optimization, because from here it is clearly visible that these steam particles are actually going outside from this location because of vacuum created here. And better to provide a vacuum at this down position. Okay, so we'll conduct this parametric study and optimization of this condensate with a new geometry, with a new video. Now finally we want to see our results from goal plots also. Before that, let us clear and hide this part. Flow trajectories, clear and hide. And finally, you want to see our goal plots. Insert goal plots, and you want to see all the 4 goals. Show. This one we have already seen, so we want to check these things in the form of graphs from history. It is showing that total pressure at the exit of cold water, it has started with 0.08, you can say 0.08, and finally it has maintained almost similar pressure. So from this one, it is showing that pressure at the exit location of cold water, we cannot see that much of variation in this cold water. Next one, you can see temperature of fluid at the exit of cold water. After 293 numbers of iterations, we can see the final temperature of cold water at exit location is 32.24 degrees centigrade. And next one, we can see the exit of hot water is almost constant. It is equal to atmospheric pressure. And finally, the temperature of steam, it was not reduced at all. After 293 numbers of iteration, we found that temperature of steam, it is 99.9 degrees centigrade approximately. Okay, so this is all about today's video. In next video, we'll come with change in geometry of this surface condenser, and next we'll go for detailed parametric study and optimization. Okay, if you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.